Okay, we are back again. So, three phase power measurement, right? So, in this case, your what we have will do it, that basically for three phase power measurement we use two wattmeter method. So, in this case we have used 3 wattmeter is given. Generally in a wattmeter you have a current coil, this is actually current coil, right, and this is sometimes we call pressure coil or voltage coil. So, load may be balanced or unbalanced, right, and this side is your if you see in your laboratory, this side when you do in the first year itself, you will see that this side is marked as M and this side is marked as L, right. M is the main side, that is the supply side, this is called main, and L is the load side, that means this side, that is why it is M and L both are marked. And this point sometimes is marked C and this point marks as V, and this is called pressure coil and voltage coil. Current coil has negligible resistance, basically current passing through, all the current passing through this your what you call this current coil, and this pressure coil actually it is a voltage coil. So, it may basically it is the voltage. So, suppose this is A and this is B, and current flowing to this, the phase A is IA, and the voltage is actually it looks the voltage from here to here is your what you call, it is your same way it is connected, we will see in the your next diagram, right. So, basically it is the line to line voltage. So, whenever this go for 2 wattmeter method, but in this diagram I have shown, just 1 minute, I have shown this your 3 wattmeters, right. So, this 1 wattmeter is redundant, it will measure 0, no need for 3 wattmeter. So, this connection I have given intentionally, just you think yourself that this wattmeter will read basically 0 if you go for a 3 wattmeter. So, basically we need 2 wattmeter methods for measuring the, and load may be star or delta, balance or unbalanced does not matter, we measure power using 2 wattmeter method, right, and this is I am leaving up to you. So, whenever you go for your 2 wattmeter method, right. So, this is my your what you call that this is my wattmeter and it measures the power P1, and load is taken as a star, say angle is Z angle theta. So, current flowing through this, actually current flowing through this is your IA, this is the phase A, and voltage measures this, right, this voltage from here to here. So, voltage actually it will be VAB. Now, from our phasor diagram we have seen that if this is my A to N, this is my your line current is equal to phase current. So, this is my VAN, right, and current this is the voltage. Here I have taken capital AN instead of small n. So, here also you can write capital AN, does not matter, and the current I actually is lagging by an angle theta, because this angle is theta, right. So, this is angle is theta. So, now this is the line voltage is VAB, leads the phase voltage by angle 30 degree. So, this is my VAB and this angle is 30 degree, right. Therefore, angle between this and this wattmeter measures actually looks the line voltage here, because it is pressure coil is connected here, it is VAB, because right, and the current flowing through this is IA. So, angle between VAB and IA is 30 degree plus theta, right. That means, this reading of the wattmeter is P1, then P1 will be equal to, it is magnitude VAB into IA into cos 30 degree plus theta, right. So, if you similarly for other wattmeter we will come to that. So, whenever you come to this one, that your this phasor diagram, if you see that VAB VN, it is 30 degree theta, angle between VAB and IA is 30 degree plus theta. Now, IA is equal to your it is VAN, actually here it is this diagram, just hold on, this diagram we know this is I have marked it capital AN, right. So, question is in between your current coil is there. So, basically this is nothing but your, you can speak small a and you can small n also, right. So, current IA actually is equal to your same actually VAN, right, divided by your Z star or ZY, right. So, this way you can make it. So, here I have written capital N, same thing. So, that means here VAN angle 0, upon Z star, right. Here also in the phasor diagram, here phasor diagram also it means your VAN. VAN, actually it is VAN, same thing, understandable, right. So, this VAN angle 0, so it is ZY is equal to Z angle theta, so it will be IA will be VAN upon Z angle minus theta. Therefore, P1 is equal to VAB IA cos theta plus 30. This is magnitude, this is magnitude. VAB actually is equal to a line voltage, so it is VL, right, it is a line voltage, and IL is equal to line current, IL is equal to IA, it is the line current, it is line voltage and line current. So, it will be VAB IA cos theta plus 30 degree, or we can write VLIL cos theta plus 30 degree. This is equation 1. This is the reading of the your wattmeter 1, right. Now, wattmeter 2, if you go to the diagram again, so in this case its voltage is what you call ABBC is marked. Let me move little bit upward, right. So, in this case your current is here, it is IC, this current is your IC, right, this current is IC, right, wattmeter is placed here. So, line current is IC and your voltage it looks as ABC, it looks as voltage CB, right. Although B to C, VBC, VAB, VBC, VC is given, but it will be VCB because this is the phase C and this is connected to B. So, voltage should be VCB, it means it sees the voltage VCB, but not VBC, right. So, and the current is IC. So, if you draw the complete phasor diagram, right, if you draw the complete phasor diagram, so this is the diagram. So, in this case earlier we have seen this is VAB, this is your VAN, this angle is 30 degree, this already we have seen before, and this is IA, right. So, IA lags from VN by theta. Similarly, this is your what you call IB, this is your IB, right. Just let me move little bit upward, just let me move. So, this is your IB, right. IB also lags from VBN by angle 30 degree. Similarly, if you see the IC also lags from VCN by IB lags from VBN by theta, and IC also lags from this one your what you call your by an angle theta, right. Now, this is, let me clear it. Now, actually diagram is hold on, I'll reduce the zoom, just hold on. So, in this case just hold on. So, in this case this is my VBC. If I want VCB, just 180 degree phase shift, just make other way, opposite way, this is my VCB, right. Now, if we want that angle should be in between VCB, IC and VCB. So, this angle, that angle between your VCB, right, and this look here, VA, your what you call VAB and VN is 30 degree. Then similarly, your what you call VCA, right, here it is VAB and VAN. Similarly, here it is VCA and VCN, angle your what you call will be 30 degree like this. So, if you look into that this is my VCN, right, this is my VCN and this is my IC. So, angle between VCN and IC is theta, because IC actually current is lagging from this one because it is balanced, say we have taken balance. So, this is angle theta, right, and angle between this thing, that your VCN and VCB is 30 degree, like your VAB and VAN is 30 degree, just we have taken the opposite, right, VCB. So, this angle is 30 degree. So, that means this angle will be 30 degree minus theta. So, this angle is 30 degree minus theta. Then wattmeter reading, for that second wattmeter reading, if P2 is given, P2 should be equal to, it is VCB, then your IC, then your cosine 30 degree minus theta, right. So, this is my VCB, but this is a magnitude, this is also magnitude. So, VCB is equal to VL, IC is equal to IL, it will be cos 30 degree minus theta, right. So, this is the reading of the second wattmeter, right. So, let me clear it. So, let me increase the zoom. So, this is what your reading of the second wattmeter. So, it should be VCB into IC into cos 30 degree minus theta, right. So, that is what has been made here. P2 is equal to VCB IC into cos your cos minus theta is equal to cos theta. So, it is written cos 30 degree minus theta is equal to cos theta minus 30 degree, right. Or we can write P2 is equal to, it is a magnitude only, line to line voltage. So, VCB is equal to VL IL cos theta minus 30 degree, this is equation 2. Then total wattmeter reading, add equation 1 and 2. If you do so, P1 plus P2 and simplify, you will see it will become root 3 VL IL cos theta, and total, that means PT actually the total power. So, it will be root 3 VL IL cos theta. This is your equation 3. This is the your whatever mathematically whatever we have derived, wattmeter is reading the same thing, it is reading the same thing, right. Similarly, if you subtract equation 1 from equation 2, right, that is equation 2 minus equation 1, you will get P2 minus P1 is equal to VL IL sin theta, right. Or if you multiply both sides by root 3, then root 3 VL IL sin theta is equal to root 3 into P2 minus P1, right. Therefore, QT is equal to root 3 into P2 minus P1, because this is my total reactive power, root 3 VL IL sin theta. So, that is my QT is equal to root 3 P2 minus P1, this is equation 4, right. Therefore, root 3 VL IL cos theta is equal to P1 plus P2 and root 3 VL IL sin theta is equal to root 3 P2 minus P1. So, divide this one, this one by this one, if you do, then it will be tan theta is equal to root 3 P2 minus 1 upon P2 plus 1. Now, if theta is positive, then it is inductive, that means if P2 greater than P1, load is inductive, if P2 less than P1, load is capacitive, right. So, if P2 minus P1 positive means load is inductive, otherwise if P2 minus P1 negative means load is capacitive, right. So, here it is given, if P2 is equal to P1 resistive load, that means theta is equal to 0, right, that means resistive load. If P2 greater than P1, it is inductive load, if P2 less than P1, it is capacitive load. So, from there you can determine, right. Now, after this you take one example, this is example 6, that wattmeter is something I have connected like this, W1, W2 and W3, and interesting thing, this thing we have intentionally taken that this load is unbalanced, because ZA is simply 15 ohm, similarly ZB is 10 plus J5 ohm and ZC is 6 minus J8 ohm. So, what we have to do is we have to measure the per phase basis, right. So, here it is unbalanced thing is given, and intentionally I have taken this example, right, intentionally I have taken this example, and this is 15 ohm, this is your 6 minus J8 ohm, that is your ZC, and this side I will show you the diagram, and this side is your ZB 10 plus J1, and one wattmeter is connected like this. Similarly, another wattmeter is your what you call connected like this, right. So, in this case your what you call, and this is the neutral. So, we want to measure your what you call the per phase power, per phase basis, right. So, this is the current IA, this is IB, this is IC, and some current is flowing to the neutral, and right, and this is your what you call unbalanced thing we have taken. Now, in this case your predict the wattmeter readings, find the total power absorbed, right. So, it is unbalanced we have taken. So, in that case your what you call that you find out your first IA, IB and IC you find out. So, it is because your what you call, it is given ACB sequence, that means balance phase voltage is 100 volt, right. If you look into that, it is given that balance phase voltage, it is given that is 100 volt, that phase voltage is balanced by ACB sequence, but load is unbalanced, So, VAN is taken 100 angle 0, and as it is ACB sequence, so VCN is 100 angle minus 120 and VBN is equal to 100 angle 120 degree, right. Now, IA is equal to, for your phase A 100 angle 0 by 15, it is 6.67 angle 0 degree ampere. Similarly, for phase B it is 100 angle 120 divided by 10 plus J5, it is 8.94 angle 93.44 degree ampere. Similarly, for phase C 100 angle minus 120 divided by 6 minus J8, it will be 10 angle minus 66.87 degree ampere, here it is, right. So, this is your find out IA is equal to VN upon this one. Similarly, for your IB is equal to VBN upon this one. Similarly, for ICN is equal to VCN upon this one. Similarly, you can find out that phase wise, right. So, once you do this, now IN is equal to minus of IA plus IB plus IC. So, if you do your IA plus IB plus IC, right, all phasor sum, if you do, it will become 10.06 angle 178.4 degree ampere, right. And for wattmeter reading power P1, it will be VAN IA into cos theta VAN minus IA. That means your, for this wattmeter, it is connected here, it is connected in this thing, and between this one and this neutral it is connected, right. So it is, what it will do, that voltage VN magnitude you will take VN, then you will take the current IA, then angle between this voltage, that is your, I write cosine of theta Vn, that is the angle of Vn minus theta of Ia, right. This way it is written just for easy understanding, right. Therefore, if you see this, that your P1 is equal to Vn Ia cosine theta Vn minus theta Ia. Theta Vn is 0, reference 1, and theta Ia also 0. So, it is becoming 667 watt. Similarly, for P2, it will be Vbn into Ib. Just look at the diagram and just write it. Cosine of, it is angle of theta Vbn is 120 degree and angle of Ib is 93.44 degree. This is a power factor angle actually, the difference is a power factor angle. So, it is 800 watt. Similarly, for P3, Vcn Ic into cos theta Vc, this is angle of your what you call that Vcn is minus 120 and angle of your Ic, it will be minus 66.87. So, here it is plus, right. So, it will become 600 watt, right. Therefore, the total power absorbed is Pt is equal to P1 plus P2 plus P3. So, 2067 watt. This is the answer, right. Now, another thing is Pt is equal to Ia square into Ra. Resistance of the phase A is Ra is your plus Ib square Rb, the resistance of your phase B, then Ic square Rc, right. If you just make all magnitude, right, so if you just put all these values, all the magnitude of this current and the resistive value, you will get 2067 watt. Here also 2067 watt. So, it is matching, right. So, answers are correct. So, hope you have understood this, right. So, example, another example you take, the 3-phase balance load in figure 29 has your Z star is equal to 8 plus J6 ohm. If the load is connected to 200 volt 200 volt lines, predict the readings of W1 and W2, also find PT and QT, right. So, it is actually figure 29. So, if we come back to figure 29, it is here. This is just hold on, I just the same figure where we have derived the formula, right. This is figure 30 and this is your, this is the figure in this figure, right. So, this is the figure, you take this figure and data are given there, right. So, we will come back to this. So, here, so the impedance is given, star connected load that is 8 plus J6 ohm and line to line voltage is 208 volt, right. We have to find out W1 and W2 and PT and QT. So, we know Z star 8 plus J6 will be 10 angle 36.87 degree ohm, right. Line voltage is 208 volt, therefore, line current will be just it is your star connected. So, your Vp upon Zy, right. So, that is your Vp phase voltage, because it is line to, it is your what you call that your line to line voltage is given 208. So, phase voltage will be line voltage by root 3 magnitude Gi, just we are making the magnitude. So, it is given 208. So, root 3 into 10, magnitude here it is 10, impedance is 10. So, IL magnitude is 12 ampere, right. Therefore, P1 is equal to VLIL cos 30 degree plus theta, and this theta is equal to 36.87 degree. So, this is your theta is equal to, here it is written here 36.87 degree. Therefore, P1 is equal to 208, current magnitude is line current we got 12, right, into cosine 30 plus 36.87 degree. So, P1 is equal to 980.48 watt. Similarly, P2 is equal to VLIL cosine 30 degree minus theta. So, it will be P2, VL is 208, IL we have got 12, 30 minus 36.87 degree. So, it is 2478.1 watt. Now we can see the P2 greater than P1 means it is inductive load, because already we have seen it is inductive only. So, P2 greater than P1, and total power PT is equal to, this is PT, total power is equal to P1 plus P2. If you add this, it will be actually 3.4586 kilowatt. You add and divide by 1000, you will get it kilowatt, right. Now Qt is equal to root 3 into P2 minus P1. So it is root 3 into P2 minus P1 will become 1497.6, because you have got P2, you make P2 minus your P1, right. You will get this directly. I am writing 1497.6 var. So it is actually 2.594 kilovar, right. And this is one exercise for you, you will do it. Answers are given, this exercise you will do it for you, right. And it is load is delta, right, and it is capacitive, so you solve it. Answers are also given, so you can verify. Now this is a very interesting problem. So just let me reduce the zoom little bit, right. So in this problem, the two balanced load are connected to a 240 kilovolt, it is frequency 60 Hz line as shown in figure 32. I will show you the figure 32. Load 1 draws 30 kilowatt at a power factor of 0.6 lagging. If 30 kilowatt is given, so from this power factor you can find out also its reactive power absorbed, right, load reactive power also, because power factor is given. While load 2 draws 45 kilowatt at power factor of 0.8 lagging, it is problem here, it is twisted. So here it is given 45 kilowatt, but power factor is given 0.8, that means here you have to find out P, and for the here you have to find out the Q, right. And therefore you have to determine first one the complex real and reactive power absorbed by the load, and B the line currents, and C the kilowatt rating of the your what you call three capacitors which are delta connected in parallel with load, right. That I will show you to raise the power factor to 0.9 lagging, and also the value of Cp, right. So this is the thing. Now question is that let us go to the your what you call the diagram. So if you see the diagram, actually this is the diagram. So question is that here little bit you have to understand, right. So loads are there. So this is the three line A, B, C, this is the three lines are there, right, and these loads are connected. This is the balanced load 1 and this is the balanced 2 loads are connected. So this is without capacitor, suppose it is connected. Now these capacitors are connected in delta form. This is given, just you see yourself that how actually things are connected, right. So now of course in the here in the problem it is mentioned that in the problem it is mentioned that your the kVA rating of the three capacitors delta connected in parallel with the load to raise the power factor 0.9 lagging. So its power factor, whatever combined power factor is given, that is different issue, but you have to raise the power factor, right. And the power factor of your what you call the first load is 0.6 lagging, and the for second load also it is your 0.8 lagging, right. So this is what you call it is given. So that is in the figure 32. This is your figure 32. So this capacitor thing we will consider later. So question is that this is my current IA, this is IA IB. So this IA, then this current is some part is going to IA1 and going to IA2. This we will see later. This we will see later, right. So question is, and this is balanced load 1, balanced load 2. So it is basically parallel circuit, right, 3 phase. It is a parallel circuit, and this is the your problem. So now very easy it is, just see. So that means your IA is equal to IA1 plus IA2, and similarly IB I see that 120 degree phase shift you can easily make out, because it is balanced system. So magnitude will be the same, right. So IA is equal to IA1 plus I2 from KCL, right. So that means so that means load 1 P1 is equal to 30 kilowatt cos theta 1 0.6, that means sin theta 1 is equal to 0.8. So S1 is equal to apparent power P1 upon cos theta 1, it will be 50 kVA, right, and Q1 will be S1 sin theta 1, it will be 50 into 0.8, 40 kilovar. Therefore P1 plus JQ1 will be 30 plus J 40 kilovolt ampere, right, in terms of kVA. Similarly for load 2, problem is twisted, right. Here it is Q2 is equal to 45 kilovar is given, we have to obtain P. So lagging power factor it is given, lagging means current is lagging. So cos theta 2 is equal to 0.8, then sin theta 2 is equal to 0.6. Therefore S2 is equal to Q2 upon sin theta 2, that is 45 by 0.6 is equal to 75 kVA, right. Therefore P2 is equal to S2 cos theta 2, 75 into 0.8, so 60 kilowatt. Therefore P2 plus JQ2 is equal to 60 plus J 45 kVA, right. Now total complex power P plus jq will be P1 plus P2 plus j Q1 plus Q2. It will become 90 plus j 85 kVA, right. Therefore, P plus jq will be, you take the square root of 90 square plus 85 square, you will get 123.8 and angle will be 43.360 degree kVA, right. So, that means it is your Vi cos theta plus j Vi sin theta form, right. So, now this is your kVA and right 123.8 kVA the apparent power. Now question is, now root 3, we know that root 3 VL IL 1 cos theta 1 is equal to PL 1 P on, right. So, IL 1 is equal to 30 we got, and this is in kilowatt, this is in kilowatt, and this your what you call is root 3 into 240 your kilovolt into 0.6, right. So, it will become actually 120.28 milliampere, right. This we have written as kilowatt. So, it is also kilovolt, right. So, if you solve it, it will be 120.28 milliampere, and theta 1 is equal to cos inverse 0.6 53.13 degree, and current is lagging. Therefore, 120.28 angle minus 53.1 degree milliampere. So, current is lagging. Similarly, for IL2 it will be 60 upon root 3 into 240 into 0.8, it is milliampere 180.42 milliampere. 60 is in kilowatt and this is in kilovolt. So, ultimately it will convert, ultimately it will become ampere. From that you write in milliampere form. It will be 180.42 milliampere, and theta 2 will be 36.86 degrees lagging. Therefore, IA2 will be 180.42 angle minus 36.87 degree milliampere, right. Therefore, total current, the KCL I told you apply, IA will be equal to IA1 plus I2. So, it will be, if you simplify, it will be 297.8 angle minus 43.36 degree milliampere, right. Therefore, IB is equal to just 120 degree phase shift, IA angle minus 120 degree. It will become 297.8 angle 163.36 degree milliampere. Similarly, IC is equal to IA angle 120 degree. It will become 297.8 angle 76.6 degree 64 degree milliampere. So, here you have got your what you call that your IA you got this IA here, and here you substitute, you are getting the magnitude will remain same, right. Now, QC is equal to this one is a very simple thing, that QC will be P tan theta volt P into tan theta volt minus tan theta nu. So, this one how we have got it, this is, look, cos theta, we want to improve the power factor to 0.9, therefore, theta nu is equal to 25.85 degree, right, and this we got it. This is a small exercise, I am leaving up to you. You please do it, right. You draw a triangle, power triangle, and from there you find out the expression of QC, right. You draw a power triangle and you do yourself. So, this one I am leaving up to you, right. So, QC will be 41.4 kilowatt, and another thing is there, the capacitor CP value not computed here, it is a delta connected capacitor. From this also you try to find out what is the value of CP, right, the capacitor in microfarad. That answer is not given here, but I suggest you please do it, and this one is a very simple thing, you do it of your own, right. Next is the measurement of reactive power using the same wattmeter, right. I mean, using your same wattmeter you measure your what you call your reactive power. In this case, let me reduce the zoom little bit. In this case, what happened that your sometimes you will find this is that current coil should be put in one phase and pressure coil should be connected across other phase, right. Sometimes we will write that your what you call wattmeter like ML, then this is your main side, this is your load side C and V. Sometimes we write like this, but as the resistance is very high, so whatever current will be flowing here, almost current will be same current will be flowing here, right. But anyway, so this current, your what you call this here, to measure the reactive power using the same wattmeter, you put the current coil in one phase. Suppose in phase A I have put the current coil which is the current IA, and the pressure coil, that is CV, it is connected to your what you call that other two phases, that is B and C, right. Then this will actually give you the reactive power. The question we have to find out how. So, this is my ZY, right. This is A and A same thing, this is actually it is same thing, it is small a, this is your small c, and this is your small v, same thing. So, IA, this same current is flowing here, IA is equal to Van angle 0, this is your Va and this is n, means small n, same thing, right. Same, I mean meaning is same, so there should not be any confusion, right. So, In will be Vn angle 0 by Zy, that this is your Vn angle 0 then divided by say Z theta. So, it will be Vn angle Z angle your minus theta, this is your Ia, right. Similarly, for Ib and Ic, now question is how it will be, if you connect this, how it, what is the value of then reactive power, how you are doing it. Then in this case you draw the phasor diagram. Now, suppose this is your VAB, this is your VAB, right, and this is my VAN, right, and current lags from Vn by angle theta, but wattmeter actually for your this thing, for this diagram, if you look into that, wattmeter sees actually the current IA, and it sees the voltage your what you call VBC, and it will take angle between VBC and IA, right, because it is seeing this spacer coil is connected across BC, so it measures the voltage VBC and the IA and the angle between the IA and VBC that we need. So, that means here in the phasor diagram, this is my VAB, this is my VAN, right, and IL lags by theta, and this is VBC, VAB, angle between VAB and VBC is 120 degree, you know. So, this your what you call between VAN and VBC angle is 90 degree, this angle is theta. So, this angle is 90 degree minus theta, right. Therefore, that wattmeter reading will be the magnitude of the VBC and magnitude of the current IA. I have put occasionally I have put bar, sometimes doesn't put bar, didn't put bar, but I told you this is magnitude, and cos, that angle between IA and VBC is 90 degree minus theta. So, cos 90 degree minus theta, that means wattmeter reading will be VL IL sin theta, right, but our reactive power is √3 VL IL sin theta, that means this reading has to be multiplied by √3 to get the correct reading, right. So, this way same wattmeter you can use for measuring the reactive power, right. So, that means the wattmeter can be so calibrated that it indicates 3-phase reactive power by having a multiplication factor of √3. That means, if you want same wattmeter the reading, that wattmeter has to be calibrated by multiplying a factor √3, that the scale is there, no, that those all these things has to be multiplied by √3. So, whatever reading you get, you just multiply by √3, you will get your what you call that your reactive power, right. So, this is the, that is why this is the connection of the wattmeter for getting your what you call that your reactive power, same wattmeter you can use. So, with this exercise is one exercise given, this problem I have got from some book. So, suppose this ABC all of a sudden this phase is opened, right. So, this is minus the 100 ohm, this is 100 ohm, and ABC all these things are given. You have to find out VOB, that what is the voltage, V open circuit voltage VOB. So, find VOB given that the system is 208 volt and ABC is equals 208 volt, means it is line to line, right, and answer is given 284 angle 150 degree volt. Answer is correct. You try to find out, very simple problem, but very interesting problem, right. Another exercise is this line currents in a 3-phase 3-wire 220 volt ABC system, IA is equal to is given, IB is given, IC is given. Find the readings of wattmeter in lines 1 A and B, and the readings if you put wattmeter in B and C and A. I mean, you connect the wattmeter in line A and B and find out the reading. You connect the wattmeter B and C, find out the reading. You connect the wattmeter A and C, find out the reading, and all these answers are given. All the and you what you call, and you find out why these readings are different, right. Now, before you are closing this 3-phase circuit, one or two things I will tell you. I mean, here itself I am telling you. Suppose sometimes it is given, suppose if it is given that impedance of a circuit, suppose if it is given that Z is equal to say √J ohm, it is given, then what is the value of R, what is the value of X, right. So, if it is given, then what is R, what is X? Suppose this is given and somebody asks you that J impedance is √/Z. So, what will be the your what you call that r value and x value. Look, j is equal to, you can write 0 plus 1 into j, this we write. That means 0 is equal to, you can write cos pi by 2, right, and 1 you can write j, this j is there, j sin pi by 2, right. That means you can write this one actually e to the power j pi by 2, right. That means my j is equal to your e to the power j pi by 2. This is class 11 complex number, right. Therefore root j means, so j, that means j is equal to the power j pi by 2. Let me clear it. That means your z is equal to root j is equal to j to the power half. So j is equal to e to the power your j pi by 2 to the power half, right, is equal to e to the power j pi by 4, right, is equal to, it is cos pi by 4 plus j sin pi by 4, right, is equal to 1 upon root 2 plus j 1 upon root 2. That means your r is equal to 1 upon root 2 ohm and your x is equal to also 1 upon root 2 ohm, right. So this is how calculate. Now another thing is with that only, suppose if somebody asks you that your what is the value of j to the power j. J we have seen, just now we have seen j is equal to e to the power j pi by 2 to the power j. That means e to the power j square pi by 2, right. That is equal to, actually j square is minus 1, so e to the power minus pi by 2. It is a real number, right. That means my j to the power j is a real number. It is e to the power minus pi by 2, right. So little bit I mean mathematical thing, just I have told you, right. So with this, thank you very much. The three phase your AC circuit part is over. Next we will take the magnetic circuits, and after that little bit of single phase transformer, then little bit of 3 phase induction machines and DC machines. So thank you very much.